just keep going.
All right, okay, so the starting point for this talk, and I think you can all agree with me, is that quantum entanglement is really a subtle notion. We know from a computational perspective that it's absolutely fundamental for quantum computation. I think it's fair to say that it's really the generating force behind all quantum computational speedups. But I think there's also still a lot we don't understand. And to sort of highlight how little we understand, in this talk, I'd like to tell you, I think a very basic property about quantum entanglement, that at least to the best of my knowledge was not known before, which is that quantum entanglement is not a feelable property of quantum systems. And this is sort of our technical term for it's not efficiently observable in a very strong sense. Which is that, in particular, in this talk, we'll construct an ensemble of quantum states that have very low entanglement with respect to a fixed bipartition of the qubits, but which cannot be, nonetheless, even though these states have very low entanglement, those states cannot be efficiently distinguished from a state with essentially maximum entanglement, even if I give the distinguisher, the quantum algorithm, as many copies as they like. Right? As long as it's an efficient distinguisher, they can't tell apart these very low entanglement states from these very high entanglement states. Okay. Right, okay, that sounds interesting, but who cares? Well, actually, our first motivation came from a topic which I think is very relevant to the theme of this workshop, which is to understand this three-way sort of intersection between entanglement, geometry, and complexity. Where of course the ADS CFT correspondence is a conjectured duality between a quantum theory of gravity, the bulk anti-de Sitter space, and a quantum mechanical system, the boundary, conformal field theory. And of course there's this Pictionary map, which takes a state or an observable in one theory to a corresponding state or observable in another theory. And a major theme in this literature, which even I know, not being an expert in this at all, is that entanglement in the CFT sort of corresponds directly to geometry in the ADS, and we see this in the Ryu-Takeyanagi formula and the ER equal EPR conjecture, and so on. It's just a major theme. It's appeared in almost all of the talks today, or yesterday. And so what we're really interested in from a complexity point of view is to try to give evidence that entanglement cannot be felt or efficiently observed. And so what we're particularly interested in then is asking, well, what if you look at the corresponding geometry? Maybe it's we're talking about the Ryu-Takeyanagi setting where you have sort of the entanglement of the CFT state corresponds to the area of some minimal surface in space-time. And what we're interested in is if the corresponding geometry ends up being feelable, right, then it seems to say something really interesting about this ADS CFT dictionary map, which is that it must be hiding a lot of complexity. It must be hard to compute. Now, the second motivation is to understand better properties of random quantum states, which are a really important computational resource. It would be fantastic if we could just get our hands on a truly random, truly Haar-random n-qubit state. But unfortunately, they're of limited practicality from a computational point of view. And the reason is basic counting arguments tell us that we need exponential size circuits to approximately prepare most states from, and that should be 0 to the n, from some simple initial state. There's just way too many n-qubit states to be prepared by a polynomial circuit. And so a lot of the quantum information literature in the last several years has been to try to get over this. And so to get over this, essential concept has been what we call pseudorandom ensembles of efficiently preparable states. So that means that you can prepare these states with a short quantum circuit, polynomial size circuit. Because of that, it's not a random state, right? It can't be if there's a short circuit, but nonetheless, these states mimic certain important properties of truly random quantum states. Now, until very recently in the quantum computing community, we've talked about information theoretic notions of pseudorandomness. like quantum 2 designs, for example, which roughly speaking is an ensemble of quantum states with the property that, no algorithm, no matter what running time, polynomial, exponential, it doesn't matter, can distinguish 2 copies of a state drawn from this ensemble from 2 copies of a truly Haar-random state. Right? So that's what a 2 design is. And this notion is now very central in quantum information theory, which with many important applications across the board. So ranging from things like randomized benchmarking, where the goal is to understand the noise in a near-term quantum experiment, to quantum advantage experiments, which essentially try to implement a approximate quantum 2 design. And then, of course, even to quantum gravity, where a quantum 2 design has been a really important model of a chaotic quantum system. Like we often use it in to model the internal dynamics of a black hole because it has very rapid scrambling properties. And now, what's interesting from a computer science perspective, though, is that pseudorandomness is also super central in computer science. But what a computer scientist generally means by pseudorandomness is actually completely orthogonal to the notion that we were talking about before, these information theoretic notions. So usually what they're talking about is computational pseudorandomness, which in the quantum context would mean this would be some efficiently preparable ensemble of quantum states that can't be distinguished from truly random states, even if you give the polynomial time observer or distinguisher in as many copies as they like. So to be really clear, there's sort of 2 major differences between this computational notion of pseudorandomness and the statistical notions or the information theoretic notions like a 2 design. The first is that we're demanding that the observer is efficient, it's polynomial time. And the second is that, so that's a weakness, that's weaker than a 2 design. But the second is that the observer can have access to as many copies of the state as it likes. Okay? So that's a stronger notion than a 2 design. And in general, this requires complexity theoretic assumptions. But classically, at least, computational pseudorandomness opens up a whole new world of applications that are not known or thought to be possible in the information theoretic setting. So things like public key cryptography, homomorphic encryption, de-randomization. These are sort of amazing computer science applications of this second notion of pseudorandomness, computational notion.
N is the number of qubits.
Yes, exactly. Okay, so our question then is going to be, what is this relationship between pseudorandomness on the one hand and entanglement on the other hand? And before our work, you might have thought that there's a very, very tight relationship. The reason is, as is well known, a typical Haar-random n-qubit state is essentially maximally entangled. It's essentially as entangled as a state can get. This is inherited by quantum T designs. So quantum T designs for any T greater than or equal to 2 are also very close to maximally entangled. And so I think our result is quite surprising. What we show is if you change the notion of pseudorandomness to a computational notion, where you have an efficient distinguisher given the polynomial number of copies, in fact, it seems like there's not nearly as strong of a relationship. So we show that computational pseudorandom states do not need to be extremely entangled.
I don't understand what you mean. A typical Haar state is a pure quantum state, so it's entropy.
Yeah, okay, good question. So what I mean is, so it's definitely a pure state. And what I mean is, cut the n qubits in half. Like you have an n over 2 qubit state, n over 2. You have a reduced NC matrix on n over 2 qubits, and look at the entanglement entropy of that. Is that better? Yeah. Okay, cool.
For a smaller subsystem, you will still have a...
Yes, exactly.
Sorry, this is relative to a fixed bipartition, or is...
Yes, a fixed bipartition, exactly. So everything we're talking about is relative to a fixed bipartition.
So if I took like a random bipartition, I wouldn't expect any of this to hold?
No, okay, so to be clear, this depends on what you mean. For our result, it only applies to a fixed bipartition. For the first 2 results, this is essentially a random bipartition. Yeah. Okay, great. So let me sketch our proof. So let me first describe the Liu and Song construction, which as far as I know is the first construction of a computational pseudorandom ensemble of quantum states. Yeah.
Can you specify that you get poly n copies?
There's more efficient algorithm. You need more than polynomial.
No, yeah. To be clear, the reason I do this is simply because I want to compare it to a true design where you're not allowed to have polynomial copies. Right. If I didn't make any restrictions whatsoever, then I could definitely say, if you have an efficient distinguisher, then clearly the efficient distinguisher can have as many copies as they want, and the polynomial number would be fine. Of course, notice obviously there's a no cloning theorem, so if the distinguisher is not going to be able to make a copy by themselves.
I was thinking if it requires more than polynomial copies, then it's not going to be efficient.
Oh, absolutely. Sorry. Certainly, we're not going to talk about more than polynomial copies if you're talking about polynomial distinguisher. Yeah, absolutely.
Okay, so we're
We're back in business? Okay, sorry about that. Okay, so what are we going to do? We're going to consider states of the following form. Now, this is the G, Liu, and Song construction. Again, it's the sort of the first construction that I'm aware of pseudorandom quantum states. So they consider states of the form psi fk, which is essentially it's an n-qubit state, and it's like a uniform superposition. Except that the binary phase, or the sign of the amplitude, is specified by a pseudorandom function, which is this fk of x. And fk of x is a very special function. We call it pseudorandom function. That's a technical term. And what it means is two things. So one, if you know the key, k, which is some classical information, you can compute the function efficiently. But if you don't know the key, then you can't distinguish the function from a totally random function with any fewer than, say, exponential number of queries. Okay? So if you know the key, it's easy to compute. If you don't, you can't even distinguish it from a truly random function.
To be clear, you can't prove that such functions exist.
No, not unconditionally, not unconditionally. But this is the basis for all of modern cryptography. Okay, now. The main result in this JLS paper is that this ensemble, size of fk, is a computational pseudorandom state ensemble, assuming that quantum secure cryptography is possible. So, assuming that a quantum pseudorandom function exists, this state ensemble is a computational pseudorandom. And that means two things, sort of correspondingly to the definition of a PRF. One, if I know the key, I can efficiently prepare the state. But if I don't know the key, then no efficient algorithm can distinguish polynomial number of copies of a state drawn from this ensemble from copies of a Haar-random. So now how entangled is the JLS construction? Well, JLS show a lower bound, and here's what they say. Suppose we consider the reduced density matrix of size of fk with respect to a subsystem on n over 2 qubits. Then the entanglement entropy of that reduced density matrix is strictly greater than log with high probability. Now, so this gives a lower bound for the entanglement. And why is this? Well, it's a simple consequence of a lemma, which says the trace of rho squared must be less than 1 over any polynomial in n. And the proof is also really simple. It's by contradiction. Say, suppose this is not the case. So suppose the trace of rho squared is greater than or equal to 1 over n to the c. Well, then the swap test, okay, so then there's an efficient distinguisher of the pseudorandom state from a Haar-random state. And the efficient distinguisher is simply a swap test on subsystem A of 2 copies of the state. If you know what the swap test is, that's great. If you don't, it doesn't really matter. The important thing is it's an algorithmic procedure that succeeds with probability proportional to trace of rho squared. So the point is that, for a Haar-random state, trace of rho squared is going to be inverse exponentially small. So if the trace of rho squared for the pseudorandom state is inverse polynomially large, then there would be a gap in the probabilities, and this would be useful as a distinguisher to tell apart the pseudorandom state from the Haar-random state. So that's not, that would be a contradiction to the pseudorandomness of the state, and therefore the trace of rho squared has to be smaller than any 1 over polynomial. And as a direct consequence of this lemma and Jensen's inequality, we have the lower bound on the entanglement entropy of the state. Okay, so we get that you must have entanglement entropy greater than log for a state. Yes.
Did we average over K when we defined this reduced density matrix?
Yes, we did. We absolutely did. Exactly. Yes. The K is the key, right? Yeah. Other questions? Okay, fantastic. Let me keep going. But we didn't know of a pseudorandom state ensemble with entanglement that saturates this lower bound until now. Okay, so let me tell you how to make a low entanglement pseudorandom state, which is the main result of our paper. So what we do is consider the JLS construction, so exactly the state construction I showed in the prior slide. And then just like before, we divide the n qubits in half, denoting the subsystems A and B. Okay. So here I'm just rewriting the JLS construction in terms of subsystem A and subsystem B. The f of ij is exactly what I called f of x before. Okay, just relabeling things in terms of the subsystem. Now, it will be convenient to think of this state as, rather than a state, as a matrix. We'll call it a pseudorandom matrix. The only thing I mean by that, it's a term we're defining, is the matrix I'll call C sub f, whose ijth entry is equal to f of ij. Okay, so in other words, the CF is the 2 to the n over 2 by 2 to the n over 2 matrix, whose ijth entry is f of ij, and we think about the rows as indexed by basis vectors of subsystem A, and the columns as indexed by basis vectors of subsystem B. Okay. So any questions about what CF is? It's just a way of encoding the state. There's nothing else there. Okay, great.
It's not the most general way you could write an entangled state in terms of the i's and the j's, right?
Absolutely, it's not the most general. It's just a way that's going to be convenient for what's next.
Okay.
In fact, the reason it's convenient is because it's not hard to see. It's the calculation you can do. That if you take this JLS state and you trace out the subsystem B, the reduced density matrix on subsystem A is directly proportional to this matrix CF. So it turns out to be 1 over 2 to the n, which is some normalization factor times CF transpose. Okay, not a calculation I'm going to do. You can do it for homework, but it's very simple. Okay. All right, so now what is our goal? So our goal is to minimize the entanglement entropy of rho, which can also be written as this 1 over 2 to the n CF transpose. Okay. Now, there's a very simple way we can do this, and this is just the high-level approach. We'll get into the details in a moment. But here's the sort of the brutalist way of reducing the entropy. Let's consider the matrix CF, and let's pick a small subset of rows, and then repeat the rows many times to get a new matrix, which we'll call CF prime. Okay, so for example, we might take the first row of CF, repeat it 3 times in the first 3 rows of this new matrix CF prime. Then we might take another row in CF, repeat it more times, and so on. I want CF prime to be the same dimension as CF, so it means that since we're repeating rows, we also have to discard rows. Okay. Now, the key point of this is that what have we done when we've repeated the row? What we've done is reduced the rank of the matrix. Okay, and so this new matrix CF prime is reduced rank, and so if I think about the new n qubit state, which I'll call psi f prime, that's the new binary phase state whose binary phase is specified by this new matrix C prime. Well, this new matrix has less entanglement entropy because it's encoded by a density matrix with lower rank. And that's a direct consequence of Jensen's inequality. We'll talk about it in a moment. But that's the basic idea. We're reducing the rank of this matrix to correspond to a new state with reduced entanglement entropy. Let's be a little bit more formal about this. So first, how do we select a subset of repeated rows? Well, the subset of rows are the rows of this new matrix CF prime are going to be selected by a 2 to the L to 1 function, which I'll call G. And what that means, what it means to be a 2 to the L to 1 function, is just that for every y, the size of the pre-image, the inverse of y is either equal to 2 to the L or 0. Okay? Now, that is, the way we're going to define CF prime, this new matrix with repeated rows, is to be the matrix whose ijth entry is the gi and jth entry of CF for all I and j. Okay, so this is a little quick, so let's just give a very simple example. If L is 1, then G is a 2 to 1 function, right? So it might look like this, then drawing the domain and the codomain of the function. right? And we think about the domain of G as specifying the rows of the new matrix, CF prime, and the codomain as specifying the rows of the old matrix. So it's really simple. We say, what is the first row of CF prime? It's going to be the first row of CF, because G of 1 is equal to 1, and so on. So that's how we're going to define CF prime. It's going to be defined by a 2 to the L to 1 function. And the matrix, CF. And then the point is, as I said before, we've reduced the rank, right? The rank of the new reduced density matrix, if I take my new state and trace out subsystem B, is equal to the rank of CF prime times CF prime transpose, which by properties of the rank is equal to the rank of C prime, which is then less than or equal to 2 to the n over 2 minus L, because that's an upper bound on the number of distinct rows that we have. And so consequently, the entanglement entropy, by a simple invocation of Jensen's inequality, is bounded by the log of this rank, which is n over 2 minus L. Okay, can I take any questions about this? It's pretty clear how I went from CF to CF prime, and then how I went to a state with lower entanglement entropy. Yeah.
How do you know that CF prime is still comes from a pseudorandom function?
Sorry?
Like, how do you know that CF prime?
How do you know that CF prime is a pseudorandom function? You absolutely do not. We're going to prove it.
Okay.
Yes, that's the whole point. Good. Okay, and that's exactly the next slide. So thank you so much. The point is, we're not done yet, because all we've done so far is, taken a state with presumably high entanglement and then reduced its entanglement by doing something with the rows of the reduced density matrix. And so we need more than that, right? We want to show that no efficient algorithm can distinguish the new state with low entanglement from the original state with high entanglement, right? And to do this, we're going to use, we're going to use a very special property. We're going to construct a very special 2 to the L to 1 function G that has pseudorandomness properties, okay? So we're going to let G be defined to be h of h prime of x mod 2 to the n over 2 minus L, where h and h prime are pseudorandom permutations. So these are like pseudorandom functions, but they're bijective. Okay, and we also know how to construct them. Okay, so 2 comments about G. So first of all, it's not hard to see that this is a 2, this is a 2 to the L to 1 function, right? But which is good. It's a good sanity check. But second, it's not hard to see that it's actually a pseudorandom 2 to the L to 1 function. Okay, so we can't distinguish it from a truly random function. And in fact, the main theorem that we prove, which I'm sort of only quoting in a little bit of detail, I won't get into it too much, is just that if a distinguisher can tell apart this new matrix C prime sub f from a truly random matrix, then the only way it can do that is either to distinguish the original pseudorandom matrix CF from a uniform matrix, and we know that it can't do that. That's not possible because of the way we chose CF, or it could distinguish this by distinguishing G, this pseudorandom 2 to the L to 1 function, from a truly random function. We also know that it can't do that because we proved that G was a pseudorandom function. Right, so that gives you a contradiction. It says that the new matrix with repeated rows must be indistinguishable from a truly random matrix, which was our goal. Yeah. Wait, sorry, uniform? Yes, it is. Exactly. Sorry, by uniform matrix, I simply mean, IID, each entry is IID plus minus 1, uniform limit. That's all I know. Yep, and yeah, true is the same thing. Yes?
Why computing the entropy is not the way to distinguish?
Because I didn't hear
Why
that.
computing the entropy is not the way to distinguish these two states?
Yes. Why is computing the entropy not a way to distinguish these two states? It's a great question. Because entropy is not something we can compute efficiently. In fact, the best handle we have on entropy is actually the swap test that I mentioned before. That's the best way we can get a sense of what the entropy of this state is. And in fact, you can take this as a proof that there's no better way to do that, in fact. Right? It's simply not accessible to an efficient observer.
It's an observer, or because of the matrix is too large?
But, it's a little hard. What I would say is because the observer is polynomial time bounded. Yeah.
And the matrix is too large.
But and the matrix is too long. To me, these are all related. Okay.
Is this swap test? I mean, could I say it like the second Rennie?
Yes, exactly, precisely. That's precisely what it is.
Okay, but the von Neumann is too hard.
Yes. Okay, great. And the point is that as long as, so we're saying that this is secure as long as this 2 to the L to 1 function G is indistinguishable from a truly random function. And that's true, it turns out, as long as we set L appropriately. So it turns out what you need is to set L less than or equal to n over 2 minus log squared, which follows from the famous quantum collision bound of Aronson and Shi. Okay, so that gives us sort of how many, what setting for L can we take before all of these things become distinguishable in the proof falsifier. Okay, all right, cool. Let's zoom back out. We're almost done. So what have we done? Well, we've shown that this new matrix with a lot of repeated rows is a pseudorandom matrix, but it has small rank. It has rank that's upper bounded by log squared of n if we take L to be n over 2 minus log squared. Okay, and so correspondingly, the binary phase state, which I'm calling psi prime, whose binary phase is specified by this new matrix C prime, is a pseudorandom state. That's the result of JLS. You have a pseudorandom function or a pseudorandom matrix, and you encode a binary phase state, you get a pseudorandom state. But the entanglement entropy of this new state, when we trace out the subsystem B, is upper bounded by log squared of n. Okay, so this is tight by the matching lower bound that we have. Right? So the point is that this is very different from the nearly maximal entanglement that we see in quantum T designs. Okay, and it's also the best we can do. It's the lowest amount of entanglement we can have before the swap test gives us a distinguisher from Haar-random. Okay. Actually, I have no idea how I'm doing with time, sorry.
Let's cut 10 more minutes.
10 more minutes, okay, fantastic. So let me just say a few things. I'll try to be quick and then we can have questions. So we can actually extend this. We can do something even better. Rather than just thinking about a pseudo-random, pseudo-entangled state, which has really low entanglement, like log squared n, we actually have a construction of a pseudo-random state so that, if you give me any parameter k, between log squared and n, we can come up with a pseudo-random state ensemble that has that amount of entanglement. Okay, so it's not just saying that we can't distinguish a very small amount of entanglement from a very large amount of entanglement. We can't just, for any bound you give me between log squared and k, I can't, I have a corresponding construction of a pseudo-entangled state with that amount of entanglement. Yeah.
You have to work harder to generate this ensemble?
Actually, yes. It's a little bit surprising, and I'm sort of going to rush over it because it's surprising, but maybe not in a super pleasant way. The main technical hurdle is that we need to prove a lower bound for how much entanglement we started with in the original pseudorandom state, and then everything else goes through once we have a lower bound. So in other words, before we didn't worry about how much entanglement we started with in the original construction because we only care about upper bound. So we're just reducing it at every step. But if you want to know, both a lower bound and an upper bound, you actually have to know how much entanglement you start with. We fix this problem by essentially using the same construction, but with a very particular PRF for which we can give a lower bound and an upper bound of around n for the starting entanglement. Okay. All right, cool. So finally, I'm ready to tell you what pseudo-entanglement means anyway. And what it means is this. So we say two ensembles of n qubit states, psi k and phi k, indexed by a secret key, are f of n, g of n pseudo-entangled if given k, both, if we're given the key, both of these states can be efficiently prepared. But if we're not given the key, then the ensembles are computationally indistinguishable. I can't tell apart which one it came from. But then the entanglement entropy between the first n over 2 and second n over 2 qubits of psi k is f of n for the first ensemble and g of n for the second ensemble. Okay, so in this language, in fact, it turns out we were the first to define this term, but in fact, this concept had been looked at before by a paper of Gheorghiu and Hoban. And in my language, in this new language, what they showed is assuming LWE is secure against quantum attack. So that's a very particular, hardness assumption, a cryptographic assumption. Then there exists n and n minus O of 1 pseudo-entangled state ensembles. Whereas our new result, and interestingly, these ensembles are indistinguishable from each other, but they are both of them are distinguishable from Haar. Whereas our new result says, assuming any quantum secure cryptography is possible, so it's a much more general assumption, we can construct states that are n and log squared n pseudo-entangled. Okay, and as a bonus, these ensembles are also indistinguishable from Haar. So we strengthen the old results in a number of different ways. Okay, let me just finish by talking about some open questions. The first one, the pseudo-entangled states that we constructed, while I found it very interesting from a theoretical point of view, it's not at all clear that they correspond to some physical system that that we would care about. And so it would be really interesting to see if we can get pseudo-entangled states from some quantum theory maybe that has a gravitational dual, maybe by evolving with the SYK model or something like this. I have no idea how to do it, but I think it's a very interesting question. Okay, and then second, I think sort of related to this point, it would be nice to talk about more than just sort of a fixed cut, to say things like, is it possible to construct pseudorandom quantum states with area law entanglement or something like this? And this requires sort of a well-defined notion of spatial geometry, which we didn't have in the state that I was talking about. It's really not very natural from a physics perspective. One of my favorite questions, we've been implementing, Google and others have been implementing random circuits, in the lab for quantum advantage purposes. Could it be that random circuits actually give rise to pseudo-entangled states, to pseudo-random or pseudo-entangled states? So, if you have a sufficiently deep, random 2D spatially local quantum circuit, and I don't tell you the description of the gates, and I just give you a polynomial copies of the state, I don't tell you it's Haar-random or it came from a sufficiently deep local random circuit. Can you tell the difference? It's not clear if that's true, but if it is, it might have nice cryptographic implications. Okay. And of course, we would like sort of more applications of pseudo-entanglement in any direction. Okay, thanks.
Yeah. A conceptual, perhaps naive question.
Yeah.
So if I have a state of n qubits that with entanglement that's log n, can't I find a state in the Hilbert space epsilon close to it with parallel entanglement?
So, okay, so actually that's a great question. I don't know the answer right off. It sounds like you should be able to. Is it? Yeah, sure.
The fact that entanglement at large n.
Right, sure.
The fact that the statement that you're saying that entanglement is not feelable, can't we just interpret that as if all I can feel is distance in the Hilbert space, I shouldn't be able to feel entanglement?
Ah, interesting. Yeah, maybe. Yes. Yeah, please.
Just to comment about the sort of physical applications of this. So I think if you have an old black hole past the page time, then effective field theory says that there should be a lot of entanglement between the interior modes and the Hawking radiation, and that the Hawking radiation should be really big. But actually, we think that's not true because the black hole has a finite entropy, and so there's much less entanglement present than we naively think. And so I think this sort of non-isometric code maybe is partly implementing this thing that you said.
Oh, wow, that would be really interesting. I'd love to talk about that more. Yeah, please.
So I was wondering if you could comment on the relationship between the distinguishability that you're talking about here and some of the other notions of distinguishability that physicists sometimes use, and like distinguishability in the context of ETH. Because there, it will definitely be a little bit more general than this one, because they're talking about distinguishability in mixed state ensembles. But I wonder if the simple operators that they talk about in the context of ETH are related to these polynomial time efficient distinguishers that you require?
That's a fantastic question. We were also interested in that sort of thing, but I don't have an answer. It would be great to look at sort of the literature and see to what degree the notions we're talking about sort of either align or do not align with previous notions of distinguishability that have been used in physics. I actually don't know.
Seems that somehow the distinguishability might have to do or be more tied to dynamics. So if I try to make a physics analogy of this, it would be, you can tell me if this is right. If I took, say, the air in this room and I replaced chucked out 9 out of 10 particles and every 10th particle replaced with 10 such things doing exactly the same thing, right? That would look like, thermodynamically it would look similar, but it would be incredibly unstable because, under evolution that would again dissipate to what we have here. So wouldn't that be indicative that a state that I just created for you is not something that's easy to construct or viable to keep?
Yeah, certainly one requirement that we had here is that we wanted the state to be efficiently constructible, right? So I'm not sure, it sounds like your model doesn't have that property, but I suppose you could think if there's sort of an analog to a cryptographic key there. That's where I'm not sure. Yes. Yeah.
I just want to comment on what Daniel said. I don't, in the fundamental description, so after your non-isometric map, the relevant subsystems are still maximally entangled for their size. So I don't think this gives an example of an application. The black hole and the radiation are as entangled as they can be.
Yeah, but someone who lives in the vault thinks they're even more entangled.
Those are different systems. I don't know how you're gonna.
Okay, why don't we discuss it offline?
I thought there were arguments of various physics style arguments that showed about random quantum circuits.
Yeah.
That showed you efficiently develop lots of entanglement.
Yeah.
Starting from a product state.
Right.
So how would you possibly generate one of these oddball states using a random quantum circuit?
No. Okay, yeah, great. No, that's not what, that was actually not what my suggestion was. It wasn't that, okay, so let me be really clear. The states that I showed in the talk is absolutely something only a computer scientist could love. Okay, that really is a strange state. It's not particularly physical. But my hope was that we could take a more physical state and use similar arguments to argue for the pseudorandomness, the pseudoentanglement of those states. So, for example, you might, my proposal here was you might imagine that I choose a circuit randomly for a certain depth, but that's the key. The description of the random circuit is the key. Right? And now I don't give you the circuit, because that's the key, of course. I give you a polynomial number of copies of the output state of that random circuit. Right? And then I ask you, is there any way that you can distinguish that from a Haar-random ensemble? Well, the answer is I don't know. But I have reason to believe that at a certain depth, the random circuit, the answer is you cannot distinguish that from Haar-random.
Right. It's some kind of design. I thought just running a given instance of a random circuit, you expect to create a volume law entanglement.
No, that's not true. That depends on the scaling of the depth with the system size.
Right. So you run, let's say you have little n qubits, you run the circuit for poly and n.
Right. But for sufficiently polynomially large depth, absolutely. Yes. So I was thinking about doing this before that.
Oh, I see. Then okay.
Yeah.
Oh, so in prior work, you had a construction of pseudorandom states that could exist in the CFP. So I was wondering if you had thought about doing similar techniques to try to make that happen.
Right. That's actually a really fantastic question that I have not thought about.
Repeat the question.
So she was saying in prior work with Umesh and Adam, we were sort of trying to argue for the existence of pseudorandom states in a physical context. And she wanted to know if we've thought about how entangled those states were. I don't know the question. Believe it or not, it's the first time I've thought of that point. I don't know.
Well, I think it would correspond to a
larger depth of the circuit, and so probably the entanglement level would be large.
Okay, yeah, I don't know. I would have to look into it, but it's a great question. Yeah. Okay, yes.
So this construction works relative to a fixed cut of
Yes,
of them.
yes.
So if you consider like a random cut, is it just that the entanglement is higher? Is that the like?
Right, exactly. So here's the thing. Yes, it could be. I don't. We played around with that idea. So what if this is same question you were saying in my language? What if the key? What if the cut is part of the key? Right. And so it's a secret. You don't know which cut has the low entanglement. We were actually not able to get very much mileage out of that idea in any direction, but it would be a fantastic open question if there's like some reason that would be more interesting.
Right.
Yeah.
Is there a quantum task that requires a certain amount of entanglement that you can kind of cheat by giving it this pseudo, like teleportation obviously won't work, but something that allows you not.
Okay, this is exactly what I meant when I said the applications of pseudo entanglement. We do have some. They tend to be applications to. They're actually no-go results for very efficient entanglement distillation protocols. Right? Why would that be? Because the whole idea of entanglement distillation is you're trying to take some messy, arbitrary entangled state and boil it down into EPR pairs. But if you try to do that with these states, then you can look at how many EPR pairs come out and then sort of we were able to give some sort of application for like an impossibility result of a very strong entanglement distillation protocol. I'm very optimistic that there will be a lot more applications, but we don't have them at the moment.
Thank you again for